Hey, this is Travis, and today I'm going to show you how you can measure the user experience of your product and then track usability improvements across subsequent versions of your product. So you can track the ROI of your design sprints and design changes that you made between different versions of your product. And right here, I'm showing you something called a usability scorecard, and it's an example of the final deliverable that we'll get out of this kind of project. Here we have three different cryptocurrency wallets. These are the products that we're measuring the user experience of. And for each cryptocurrency wallet, we take measurements on 5 tasks. And then also get a system usability score for each of the wallets, right? And we take 2 measurements per task. We take the percent of users who successfully completed the task and the average time that it takes users to complete that task. What we're going to do in this project is mix in something called inferential statistics. Inferential statistics is the basis of social science research. It is, in this example, we are sampling users from a population of overall users. There's a population of overall users for MetaMask. It could be hundreds of thousands or millions of people, but we actually just take a 15 user sample of that population, and then using inferential statistics, we can relate the sample measurements back to the actual population values that we're trying to estimate. And again, inferential statistics gives us this ability to do so through 2 things. We can calculate confidence intervals, and this tells us the precision or confidence that we have in our sample measurements and how they relate back to the true population value. And then we can do something called hypothesis testing, where so an example of hypothesis testing is if we look at MetaMask on task 1, we have 60% completion for MetaMask, Argent 93 completion, and Coinbase 87% completion. Now, are these differences in completion rates, are they real differences that we would expect in the population? Or are these differences just due to noise in our sample? We don't really know until we do something called a hypothesis test or a stat test. And we're testing for statistically significant differences. And just a hint right here, I have this shown in red because indeed 60%, and we did a stat test on this, which I'll show you later on, but 60% is indeed less than 93% and 87% at the 85% confidence interval. So no problem if you don't understand any of that. I'm just trying to give you at a high level what we're going to be doing with this kind of stat testing. But anyway, this is the final result that we'll have, where we'll have usability measurements for each task on each product, and we're going to be comparing them across products. Okay, I want to talk a little bit more about inferential statistics. It is really the basis of all social science research, and even engineering disciplines use it as well. The idea is that we can take a sample from an overall population and take measurements on this sample, which is just a subset of users or customers or people from the population. And then we can make claims about the population based on our sample measurements. And inferential statistics gives us the means of doing this. We can calculate something called confidence intervals where, for example, like the SUS score for MetaMask is 52, and we calculated the confidence interval to be between 46 and 59, right? So this gives us a level of precision when we're presenting the sample measurements back to stakeholders. And just at a really high level for now, the larger the confidence interval, the less precise our sample measurements are. And the smaller the confidence interval, it's vice versa. The more precise our measurements are thought to be. So this is a way, an example of how to use confidence intervals in relating a sample measurement back to a true population value, which is really all that we're interested in. And again, and then as I told you before, showing you on the usability scorecard, we have something called hypothesis testing. So with hypothesis testing, it allows us to search for statistical significance and look for actual differences in user populations, like between two user groups, like for MetaMask versus Argent versus Coinbase, and to determine with statistical confidence if there are indeed or in fact differences between these populations, or if the differences that we observe are small and only really attributed to noise and error in the data. It's brought in through something called sampling error. Whenever you take a subset of the population, you introduce something called sampling error, and it's just unavoidable. Obviously, a subset of the population is only ever going to be an approximation of the population. So that's why error is introduced, and we need something like inferential statistics to help us gauge that error and really understand what we can say about a population based on our sample measurements. So kind of all that dry stuff is out of the way, but inferential statistics is pretty cool and very important and fundamental. Now let's talk about a usability test. Usability tests, there are many different kinds, and we are running something called a comparative and summative usability test. It's comparative because we have 3 products, and in the end, as I showed you before, we're going to be comparing usability measurements across these 3 products. It is called summative because we have predefined tasks and metrics that we want to measure, like completion rate and time on task. And so we're evaluating the performance of these products in a quantitative way. On the other side of the spectrum is something called formative usability testing, which is much more discovery-based and qualitative. We might take users through general areas of the app and observe them and ask questions and try to uncover pain points, as many critical pain points as possible. And this is qualitative. It gives you qualitative usability issues, and it's great. There's a time and a place for it. But especially when we want to apply inferential statistics and quantitative analysis to our studies, summative is a great type of usability test. And throughout this project, I list several really good references for statistics resources. One of them is called Measuring the User Experience by an author whose last name is Toulis. I think his name is Tim Toulis. And he really just wrote a great book about summative usability tests. And he talks about 3 different categories of variables or questions that you can ask in a test. Well, in generally, so when we think of a summative usability test, we're evaluating a product on some predefined measurements. So we create an overall task list of the tasks that we want to evaluate these products on, and this kind of breaks down how the usability test is going to go. So in this case, we have, I'm kind of jumping ahead here, but we have 5 tasks and a post-session questionnaire called the System Usability Score, which is just 10 basically survey questions. And that will be the extent of our usability test. Okay, so anyway, the 3 categories of questions you can ask in usability tests are task performance metrics, post-task ratings, and post-task questionnaires. So yeah, we're going to give an SUS at the end and take completion rate and time on task measurements for each task for each product. Now we're on to talking about sample size, and we can use inferential statistics to come up with a reasonable sample size that we need. Of course, we don't want to sample more people than we would need because it's a waste of resources. So as a researcher, we need to decide on the precision that we need in order to find statistically significant differences and then calculate the minimum sample size required to achieve that precision. And I won't go into detail about how this is done, but Jeff Sorrow writes a really comprehensive, thorough explanation for how to do this in his book, Quantifying the User Experience, another great resource for what we're doing. Anyway, long story short, what we're going to do is, well, in order to get the precision that we need a sample size of 15n, 15 users. Now we come to something called a study design or experimental design. There are several ways that we can do this, right? Let's talk about the two main ones. Something called a between subject study design and a within subject study design. So a within subject study design takes every single user and shows each user each of the three products. So each user will do the 5 tasks for MetaMask, 5 tasks for Argent, and 5 tasks for Coinbase, right? And we only need 15 people for that. Between subject only shows one product to one respondent. So we have a group of users who only see MetaMask. We have another group of users, a separate group or an independent group that only see Argent, and then we have another independent group that only sees Coinbase. I like between subject more. If you think about it, within subject can bias the users because they are seeing 3 products. So if let's say like the users do the first 5 tasks on MetaMask, and then we show them Argent, well, they might have better performance on Argent and Coinbase just because they came after MetaMask, and maybe they learned the tasks in the previous, when testing the previous products. So there's kind of some weird biases that get introduced within subject. So that's why I prefer between subject. Of course, there are pros and cons. The con to between subject, though, is that we are essentially dividing our sample size into 3 different separate groups. So instead of 15n for the entire study, we actually need 15n times 3 to still achieve the precision I talked about above and execute the between subject study design. So 15n for MetaMask, 15n for Argent, and 15n for Coinbase. So the last thing about inferential statistics is that our sample needs to be representative of the population. Let's say the average age of our sample is 50, and the average age of the population of cryptocurrency wallet users is 25. So these are very different groups already. Like, our sample is much older on average than the average of the population. And you could make the argument that the sample isn't representative of the population that we're interested in. So this could compromise the validity of our measurements in the sample. 50-year-olds probably use cryptocurrency wallets differently and might have different performance measurements than 25-year-olds on average, right? I know we're just talking about averages here, but it's not hard to imagine that those are different things, and that affects the validity if your sample does not truly represent the population. So in order to get a representative sample, what you need to do is randomly sample or draw users from the population, and doing so should give you representation. There's always going to be some kind of sampling bias that gets introduced into things. Like really well-known sampling bias is the fact that females are more likely to take and complete surveys than males. So just based on gender, you're going to over-index on females as opposed to males, and this is something that you need to control. If you, for instance, if the population you're interested in is more heavily male, which I would assume that cryptocurrency wallet users is. Let's say cryptocurrency wallet users, that population might be 80% male. So we would want, ideally, our sample to be 80% male as well. And again, there are other variables, important variables that you might want to consider when creating a sampling plan, like you want the age to match, you want gender to match, you want technographics to match and other demographics. And so it can start to get complicated. And you don't have to worry too much about like some abstract variables that we could probably think of. But these are important considerations. And when you're putting together a sampling plan, you can always seek the counsel of a recruiting agency or a panel house. And they run into these logistical problems all day. Trying to get the most representative, highest quality sample for people. So I would seek their counsel when you're creating a sampling plan. Anyway, the 5 tasks that we're going to test for each product is going to be task 1, set up the app. So kind of sign up, maybe create your account, that kind of thing. Task 2, deposit crypto in wallet from a centralized cryptocurrency exchange. Task 3, send crypto to a friend. Task 4, connect a hardware wallet. Task 5, connect Aave, which is a DApp, to the hardware or to the crypto wallet. And then we're going to give a 10-question post-session survey, which is called the System Usability Score. Awesome. All right, now we're into the analysis. Now that we've collected the data, let's talk about the different variables that we have in this data set. So this is the final data set. We have a completion rate and the time that it took them to complete the task for each task, right? Task 1, 2, 3, 4, 5, and then an SUS score, and then which product they were rating. So again, we have 15 users who saw MetaMask, 15 who saw Argent, and 15 who saw Coinbase. Let's talk about the different types of variables that we have. The completion rates are something called discrete binary variables. They are either pass or fail. And the time is the elapsed time from beginning to end of the task in terms of seconds. That's what it's measuring. This has implications for how we conduct stat testing because different stat tests are used for these different variable types. So we break this analysis into 2 major sections. The first is stat testing on the completion variables because they're discrete binary variables. And you can summarize these. Just think about the difference in how you'd summarize these, right? For a discrete binary variable like this, we're going to be interested in the proportion of users who completed the task. We call this the completion rate. So look, I've got 40, we're going to have 15 users of each of these, and we're going to calculate a proportion for how many passed and how many failed. And then also for time, this is a continuous variable, and you would take the average of it, right? It's like any other numeric continuous variable. You have descriptive statistics like standard deviation, average or mean, geometric mean, median, those sorts of things, and that's what we'll use to describe the time variables, which are continuous. Yeah, so here's just an example of how we can summarize these, right? So this is for task 1. For Argent, 93% completion rate, average time on task, 188 seconds. And then for Coinbase and MetaMask. And Jeff Sorrow, in his book, Quantifying the User Experience, gives an awesome roadmap for the types of statistical tests that you use for testing for significance and calculating confidence intervals for the 2 different data types. So this first map is for continuous data, like our time variable, and SUS variable, by the way, which I didn't mention above. And then discrete binary data here, right? So those will be helpful for you. So we start with completion rates. And with these, we calculate something called a contingency table for each task. What a contingency table is it has the products or the crypto wallets in the rows, and then it has the outcome variable in the columns. And we are writing in here the frequencies of occurrence. So for MetaMask, 12 people passed. I'm printing task. This is the contingency table for task 5, by the way. So for task 5, 12 users successfully completed task 5 for MetaMask. Argent, 6 users completed task 5. Coinbase, 12 users completed task 5. And what we're doing is we feed these contingency tables into something called a Fischer exact test. So the Fischer exact test tells us whether or not the product variable is independent from the pass-fail variable. In other words, are these frequencies what we would expect if these two variables are independent of each other, right? Is the completion rate for task 5 independent of the product, or do all the products have similar, relatively similar completion rates? Again, this is what stat testing does. It allows us to tell if there are differences between these products in terms of completion rate, true differences, and not just differences from noise in the sample. So we run a Fischer exact test for each of the 5 3x2 contingency tables. And that corresponds to each task. So for task 1, we have a p-value of 0.10. So basically at the 89% confidence level, there is a difference. There is a statistically significant difference somewhere on task 1 between the products and the completion rate. Task 2 has a very high p-value, so there is likely no difference. Task 3, 0.166, right? And then 4.004, and then 5.04. Okay. So definitely on task 4 and task 5, they have small p-values, which indicate that there could be a relationship between the product and completion rate. Well, we don't know, since there are 3 products, we don't know which over-indexes over what or under-indexes over what. So what we need to do now is follow up with something called with pairwise Fischer exact tests, where we measure for statistical significance between each pair in each task, each pair of wallets within each task. I'll show you that later on. These Fischer exact tests also allow us to calculate confidence intervals around the point estimate. So for task 4, here's the point estimate. 82% completion for MetaMask, Argent 59% completion, Coinbase 29% completion. Wow, those do look like pretty big differences. And we can look at the confidence intervals here that we calculated using the Fischer exact test. And again, the confidence interval is telling us the precision of our sample measurements, or these point estimates here, in relating it back to the true population value. If we could survey or measure the completion rate for task 4 with all of the users, then we wouldn't need inferential statistics. But since this is a sample of only 15N for each product, then we have a confidence interval. And the confidence interval literally means, right up here, the range of possible estimates that we would expect to see 95% of the time if we repeatedly estimate a statistic using random samples from a population. So we have a population of we have a sample of 15 users for MetaMask. And the confidence interval is 69% to 96%. If we replace that sample back into the population, and then randomly drew another 15, and then randomly drew another 15 and took a measurement on task 4, and then randomly sampled another 15 and took a measurement on task 4. So we keep doing that, and we would expect 95% of those measurements to fall in the 69 to 96% range. And that is literally how a confidence interval is interpreted. And so it's a little backwards and confusing, and they're really subject to misunderstanding confidence intervals. But that's the technical way of describing a confidence interval. And really all that stakeholders need to see is that range. And again, the range is telling us the precision of our sample measurements related back to the true population value that we're estimating, the larger the confidence interval, the less precision, and then the smaller confidence interval, the more precision. And by the way, if you want to decrease confidence interval, then you can either decrease confidence level or you can add more sample and collect more data, and we would be more precise with more data, for instance. So we calculated completion rate. We have a point estimate for each one. And then we have these blue bars here are the confidence intervals. So 15, remember, so this is for Argent 59, and then the confidence interval, yeah, that matches this right here, 59. And then confidence interval is from 42% to 76%. Cool. I think that these charts are good to show stakeholders. It's probably a good thing to have in the appendix for a more technical, detail-oriented stakeholder. The usability scorecard is probably the extent that I would go in terms of technicality when presenting it to the main, more executive stakeholders. Okay, again, like I said before, we did Fischer exact test on the 3x2 contingency table, and it tells us if something is different within the tasks, but we don't know which wallets are different from one another for each task. So we follow up with pairwise Fischer tests. And for example, right here, here's a Fischer exact test for MetaMask versus Coinbase on task 4, and we get 0.002 p-value. So for sure, MetaMask and Coinbase are different from one another on task 4. Slightly higher p-value, 0.2. So, around the 80% confidence level, there is significance. But again, since our threshold right now is at 95, well, actually technically we're at 85, then we would say that there really isn't a statistically significant difference here, just due to the lack of statistical evidence. And then here we see Argent versus Coinbase. Kind of a smaller p-value, 0.13. So at the 86% confidence level, there is a significant difference between Argent versus Coinbase. And remember, look, Coinbase is 29, Argent is 59, and MetaMask is 82. So this difference, 82 minus 29, is a much greater gap than 59 minus 29. And that's why, without a doubt, there is a significant difference between MetaMask and Coinbase, but we do see a slightly higher p-value for the Argent to Coinbase comparison. Let's do the same thing for task 5. Task 5 completion rate, Argent 41, 76, 76. And then follow up with pairwise tests to find statistical significance. And we see that MetaMask versus Argent and Argent versus Coinbase are significant at the 94% confidence level. And at this point, I'm saying, because usually the standard for confidence levels is 95. At this point, I'm saying let's drop down to 85. We don't need to be like super certain about these results. This is what we get when we have 15N sample size for each group. So let's decrease the confidence level at 85 so we can take some of these slightly higher p-values as significant that we saw above. I'm going to summarize everything in a second, but we're going to do the same thing for task 1, 2, and 3. Now I want to retest them now that we're at the 85% confidence level and just get all the visuals just to be thorough, because we're going to include these in the appendices or in the appendix. Task 1, 88, 82, 59, right? So, if I had to guess, we're not going to be able to tell a difference between Argent and Coinbase, but there will be significance at least between Argent versus MetaMask, 88 minus 59. That's a relatively large gap. And, we can see visually that, look, we're not going to tell a difference between Argent and Coinbase. Look how much the 85% confidence intervals are overlapping one another. Same thing for task 2, not much here at all. And if you remember the 3x2 Fischer exact test that we did above for task 2, it had a p-value of 1, which is it's the highest p-value you can have. which means that there really is not a statistically significant difference on between any of the products for this task. In task 3, yeah, looks like there could be some differences between Coinbase and MetaMask. So we follow up and we see, and again, we're at the 85% confidence level, so we're looking for p-values of 0.15 and below. And I don't think that I've explicitly said this yet, but the relationship between p-value and confidence level is p-value equals 1 minus confidence level. So 0.15 is corresponds to the 85% confidence level. So on task 1, there is a difference between MetaMask and Argent. On task 3, there's a difference between MetaMask and Coinbase. And that is all. Okay, so let's summarize what we have so far. For task 1, Coinbase equals Argent, and both of these are greater than MetaMask at the 89% confidence level. There is no statistically significant differences on task 2. On task 3, Argent equals Coinbase, and both of these are greater than MetaMask completion rate for task 3. Task 4, MetaMask is greater than Coinbase, and Argent is greater than Coinbase. And then task 5, Coinbase equals MetaMask, and both of these are greater than Argent. And these are the final results that we're going to show for completion rate in the usability scorecard. We're going to show the point estimate of completion rate for each wallet, and then we're going to mark these statistically significant differences with colored boxes. So when something under indexes like MetaMask is below Coinbase and Argent for task 1, if you remember from the very beginning of this video, we had a red box around the point estimate for MetaMask. And that is how we explain to the stakeholders that MetaMask has a relatively lower task 1 completion rate. So potentially, if we're the MetaMask product team, this is something that we need to work on in the next version or release of our product. Cool. Awesome. And yeah, again, here are I'm just summarizing the point estimates which make their way into the usability scorecard. Now, that is the section for the discrete binary variables, or the proportions or frequencies, or whatever you want to call it. And we used Fischer exact tests to calculate confidence interval and to do hypothesis testing for those. Now let's move on to the time variables and the SUS variable, which are numeric and continuous variables. And for these, we use something called ANOVA and t-tests. ANOVA is great. It is the same thing, basically the same as the 3x2 Fischer exact test above. ANOVA is testing, and by the way, it stands for analysis of variance. ANOVA is testing for if there is a difference between the time measurements between at least two of the wallets, right? So if there is some difference in the group of wallets, then it's going to return a significant p-value. And then what we're going to do is follow up with something called t-tests for pairwise comparisons. So for each wallet pair in each task, we're going to run a t-test on it, and these tell us if there, it actually will tell us if there is a difference between those two wallets that we're testing. Again, this is the same process that we used above. We started with a group level comparison, got a p-value, could see if there was any significance at that group level. And then if there was, then we could follow up with a pairwise Fischer exact test. Now we're doing the same thing here. ANOVA for group level comparison and t-test for pairwise comparison. Something interesting actually for these time variables are generally positively skewed. It means there's a right tail. So this is the distribution for the task 1 time on task variable. And as you can see, it's positively skewed, meaning that that longer task times, people stack up here at longer task times. There's a tail or a distribution, and there's actually quite a few in that 350 to 400 bucket there. This is really the case for all task times. There are going to be outliers that skew the mean of the distribution to the right. It's skewing the mean to a higher task time, especially if we removed these outliers over here. Like, I don't know why they're here. Then the mean could be significantly different. So what Jeff Sorrow, and again, the book Quantifying the User Experience, what he recommends is to use something called the geometric mean, which is more resistant to outliers than the mean. So we do that. And what the geometric mean is you log transform all of the time variables. You take the mean of those transformed time, and then you exponentiate the mean to return back to the original scale, and that is the geometric mean for a time variable. And we do that for each of the tasks, for each of the variables, right? And for SUS, it is a continuous variable like time, but it's not positively skewed like time. So we just calculate the mean for that, and this is what we use for the point estimates. Geometric mean for the time variables, and just regular mean for the SUS score. I'm using a t-test here to calculate the confidence interval for each of these, by the way. And just like we did with the proportions data above, I use bar charts where I'm showing, again, this is the geometric mean for task 1, and then the confidence interval around it at the 85% confidence level. And look at this, we can see that these are all pretty much going to be statistically significant from one another, because look at these, the 85% confidence level, look how small that range is there. These don't overlap at all. Yeah, and again, these are in seconds for how long it took users to complete each of these tasks. And then this sixth visualization here is the SUS score. And these really don't look like they're overlapping at all. But again, like, we want to be rigorous in our approach to this, and instead of eyeballing it, we apply stat testing to determine if there is significance. So we start with something called analysis of variance, or ANOVA, on each of the tasks, and we can see, look how small that p-value is, that there is significant difference on task 1. There is on task 2, there is on task 3, there is on task 4, and there is on task 5. And then there is on the SUS score. So now that we know that there is significance on those tasks, now we have to go in and do pairwise t-tests, which does a t-test between each pair of the 3 wallets for each task. Sorry, that's a little backwards way to say it. But Argent, Coinbase, small p-value. Argent, MetaMask, small p-value. Coinbase, MetaMask, small p-value. So they're all statistically significantly different from one another. And they are for everything. At the 85% confidence level, basically all of these p-values for the pairwise tests are less than 0.15. Therefore, we have differences on these time variables across each wallet. And again, we're going to summarize this in the usability scorecard, and these are the point estimates that we're going to use. Remember, geometric mean for time, very important, and then just regular mean as a point estimate for the SUS. And now we're back to the usability scorecard. So let's look at what this is telling us. MetaMask under indexes is lowest for task 1. Argent and Coinbase are not differentiated from one another. MetaMask has the largest time on task. Argent comes in the middle, and Coinbase is the lowest at 121. Same kind of relationship. Well, yeah, slightly same. Like, it still has. So MetaMask is 51 seconds. That's the quickest or the best performance for task 2. Argent slowest on task 2. MetaMask somewhere in the middle on task 2. And remember, we can't differentiate completion rates from one another. We don't think that these are real differences, that real differences exist in the population, at least at our 85% confidence level. So we don't mark any of this. So to stakeholders, we would say that the 3 cryptocurrency wallets perform equally well in terms of completion rate on task 2. That's the way to interpret this. On task 3, again, MetaMask has the worst completion rate on task 3, sending crypto to friends, although Coinbase is slowest for how to send, for sending crypto to friends. Task 4, MetaMask has the highest completion rate and the quickest time for connect to hardware wallets, so they're definitely winning here, doing really well. And Coinbase has the lowest completion rate at only 27% of people. And remember that this 27% is just a point estimate. There's a confidence interval associated with every single one of these measurements that you see on here. And I just didn't want to overcomplicate this visual, but maybe you do want to report the confidence intervals to your stakeholders. Like, it's 27%, or it's between like 12 and 52%. I'm not sure what the confidence interval is. I'm just guessing. Anyway, same type of analysis for task 5, and then SUS, same type of analysis. Coinbase has the highest SUS, then Argent, and then MetaMask. So overall, Coinbase is winning, and we can pretty much see that. I mean, they have relatively high completion rates on everything except for the Connect hardware wallet, which, wow, that takes a lot of time for the people who do complete it. And so it kind of makes sense to me. And it does make sense that the SUS is the worst for MetaMask. Because they have, like, on pretty basic stuff, like just setting up the app and sending crypto to a friend, they have relatively low completion rates there. So something to think about if we're the product managers. Thank you.